Hello friends, welcome to this YouTube channel. Today we are going to solve a pair of numerical problems on three-phase induction motors. By solving these problems, we shall learn how to determine output power and overall efficiency of a three-phase induction motor for a particular value of slip using its per-phase approximate equivalent circuit when values of circuit parameters are given. A three-phase 500 volt 50 Hz star-connected induction motor has a per-phase stator impedance of 0.062 plus J times 0.21 ohm. The equivalent rotor impedance per phase at standstill is the same. The magnetizing current is 36 ampere. The core loss is 1500 watts and the mechanical loss is 750 watts. If the motor operates at a slip of 2% at rated voltage and frequency using approximate equivalent circuit, we have to determine input line current and its power factor, output power and overall efficiency. Let us first write down the given data. Line-to-line terminal voltage VL equals to 500 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 500 divided by root 3, that gives us 288.675 volt. Stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.062 plus J times 0.21 ohm. According to the problem statement, standstill rotor impedance per phase referred to the stator Z2S dash equals to R2 dash plus JX2S dash equals to Z1, that is equal to 0.062 plus J times 0.21 ohm. At any value of slip S, rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 2%, that is equal to 0.02 per unit. Therefore, Z2 dash equals to 0.062 by 0.02 plus J times 0.21 ohm. That gives us 3.1 plus J times 0.21 ohm. Let us now calculate equivalent impedance per phase. ZEQ equals to Z1 plus Z2 dash. Using values we get 3.162 plus J times 0.42 ohm. This may be written in polar form as 3.1898 ohm at an angle 7.566 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 288.675 at an angle 0 degree divided by 3.1898 at an angle 7.566 degree, which is approximately equal to 90.5 ampere at an angle minus 7.566 degree. Given magnetizing component of no load current per phase Im equals to 36 ampere. Expression for core loss Pc equals to root 3 times VL into IW. Therefore, working component of no load current per phase IW equals to PC divided by root 3 times VL. Given coal loss PC equals to 1500 watts. Therefore, IW equals to 1500 divided by root 3 times 500, that is equal to 1.732 ampere. Expression for no load current per phase I0 equals to IW minus J times IM, that is equal to 1.732 minus J times 36 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 90.5 ampere at an angle minus 7.566 degree. This may be written in Cartesian form as 89.7121 minus J times 11.916 ampere. Applying Kirchhoff's current law at node P, we get input current per phase I1 equals to I0 plus I2 dash. Using values, we get 91.4441 minus J times 47.916 ampere. This may be written in polar form as 103.2374 ampere at an angle minus 27.6542 degree. Given slip S equals to 0.02 per unit and per phase rotor resistance referred to stator side R2 dash equals to 0.062 ohm, we have determined rotor current per phase referred to stator side I2 dash equals to 90.5 ampere. For three-phase induction motor, expression for total air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Using values, we get 3 into 90.5 square into 0.062 by 0.02, that is equal to 76,169.325 watt. Now we shall calculate total mechanical power developed. Pm equals to 1 minus S times Pg. Using values, we get 1 minus 0.02 into 76,169.325, which is approximately equal to 74,646 watts. Let us now determine total output power. PO equals to PM minus PR. Given mechanical loss, PR equals to 750 watts. Therefore, PO equals to 74,646 minus 750, that is equal to 73,896 watts. Since 1 bhp equals to 746 watts, PO equals to 73,896 divided by 746, which is approximately equal to 99 bhp. Given per phase stator resistance R1 equals to 0.062 ohm, we have computed input current per phase I1 equals to 103.2374 ampere. Let us now calculate stator copper loss. PS copper equals to 3 times I1 square into R1. Using values, we get 3 into 103.2374 square into 0.062, which is approximately equal to 1982.381 watt. Given coal loss PC equals to 1500 watts. Since rotor coal loss is negligible, we can write stator core loss PSI equals to PC, that is equal to 1500 watts. Let us now determine total stator losses. PS equals to PSI plus PS copper. Using values we get 1500 plus 1982.381, that is equal to 3482.381 watt. Let us now determine total input power. Pin equals to PG plus PS. We have obtained total air gap power PG equals to 76,169.325 watt. Therefore, Pin equals to 76,169.325 plus 3,482.381. That gives us 79,651.706 watt. In polar form, we can write input current per phase I1 equals to I1 at an angle minus phi 1 equals to 103.2374 ampere at an angle minus 27.6542 degree. For star-connected induction motor, input current per phase equals to input line current. Let us now determine input power factor. Cos phi 1 equals to cos of 27.6542 degree, that is equal to 0.886, lagging. Let us now determine overall efficiency of the motor. Eta equals to PO divided by Pin. We have computed output power PO equals to 73,896 watts and total input power Pin equals to 79,651.706 watt. Therefore, eta equals to 73,896 divided by 79,651.706, that is equal to 0.92774 per unit or 92.774%. A 3-phase 6-pole 15 HP 220 volt 60 Hz star-connected induction motor has following per phase parameters referred to stator side. R1 equals to 0.128 ohm, X1 plus X2S dash equals to 0.496 ohm, R2 dash equals to 0.0935 ohm, RC equals to 183 ohm, and Xm equals to 8 ohm. The rotational losses equal to stator hysteresis and eddy current losses. When the motor operates at a slip of 3% using approximate equivalent circuit, we have to calculate input line current and its power factor, output power, and overall efficiency. Let us first write down the given data. Line-to-line terminal voltage VL equals to 220 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 220 divided by root 3, that gives us 127 volts. Given stator resistance per phase R1 equals to 0.128 ohm and rotor resistance per phase referred to stator side R2 dash equals to 0.0935 ohm. At standstill condition, total leakage reactance per phase referred to stator side X1 plus X2S dash equals to 0.496 ohm. For any value of slip S, equivalent impedance per phase ZEQ equals to R1 plus R2 dash by S plus J times X1 plus X2 S dash. Given slip S equals to 3%, that is equal to 0.03 per unit. Therefore, ZEQ equals to 0.128 plus 0.0935 by 0.03 plus J times 0.496 ohm. That gives us 3.2447 plus J times 0.496 ohm. This may be written in polar form as 3.2824 ohm at an angle 8.6912 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 127 at an angle 0 degree divided by 3.2824 at an angle 8.6912 degree. That gives us 38.6912 ampere at an angle minus 8.6912 degree. Let us now determine stator core losses. PSI equals to 3 times ET square by RC or VL square by RC. Given per phase resistance representing core losses, RC equals to 183 ohm. Therefore, PSI equals to 220 square divided by 183, which is approximately equal to 264.48 watt. Now we shall calculate working component of no load current per phase. IW equals to ET divided by RC. Using values, we get 127 divided by 183, that is equal to 0.694 ampere. Now we shall calculate magnetizing component of no load current per phase. Im equals to ET divided by Xm. Given per phase magnetizing reactance, Xm equals to 8 ohm. Therefore, Im equals to 127 divided by 8, that is equal to 15.875 ampere. Expression for no load current per phase I0 equals to IW minus J times Im, that is equal to 0.694 minus J times 15.875 ampere. Given slip S equals to 0.03 per unit and per phase rotor resistance referred to stator side R2 dash equals to 0.0935 ohm. We have determined rotor current per phase referred to stator side I2 dash equals to 38.6912 ampere. For three-phase induction motor, expression for total air gap power PG equals to 3 times I2 dash square into R2 dash by S. Using values, we get 3 into 38.6912 square into 0.0935 by 0.03, which is approximately equal to 13,997 watts. Let us now calculate total mechanical power developed. Pm equals to 1 minus S times Pg. Using values, we get 1 minus 0.03 into 13,997, which is approximately equal to 13,577 watts. According to the problem statement, rotational losses PR equals to PSI. We have computed stator core losses psi equals to 264.48 watt. Therefore, PR equals to 264.48 watt. Let us now determine output power. PO equals to PM minus PR. Using values we get 13,577 minus 264.48, that is equal to 13,312.52 watt. We have determined rotor current per phase referred to stator side I2 dash equals to 38.6912 ampere at an angle minus 8.6912 degree. This may be written in Cartesian form as 38.2469 minus J times 5.8466 ampere, and no load current per phase I0 equals to 0.694 minus J times 15.875 ampere. Applying Kirchhoff's current law at node P, we get input current per phase I1 equals to I0 plus I2 dash. Using values we get 38.9409 minus J times 21.7216 ampere. This may be written in polar form as 44.5895 ampere at an angle minus 29.1532 degree. Let us now calculate stator copper loss. PS copper equals to 3 times I1 square into R1. Given per phase stator resistance R1 equals to 0.128 ohm. Therefore, PS copper equals to 3 into 44.5895 square into 0.128, which is approximately equal to 763.48 watt. Now we shall compute total stator losses. PS equals to PSI plus PS copper. We have obtained stator core losses PSI equals to 264.48 watt. Therefore, PS equals to 264.48 plus 763.48, that is equal to 1027.96 watt. Let us now determine total input power. Pin equals to PG plus PS. We have determined total air gap power. PG equals to 13,997 watts. Therefore, Pin equals to 13,997 plus 1027.96. That is equal to 15,024.96 watt. In polar form, we can write input current per phase I1 equals to I1 at an angle minus phi 1 equals to 44.5895 ampere at an angle minus 29.1532 degree. For star-connected induction motor, input current per phase equals to input line current. Let us now determine input power factor. Cos phi 1 equals to cos of 29.1532 degree, that is equal to 0.8733 lagging. Let us now determine overall efficiency of the motor. Eta equals to PO divided by Pin. We have obtained output power PO equals to 13,312.52 watt and total input power Pin equals to 15,024.96 watt. Therefore, eta equals to 13,312.52 divided by 15,024.96, that is equal to 0.886 per unit or 88.6%. So today we have solved a pair of numerical problems on three-phase induction motors. By solving these problems, we have learned how to determine output power and overall efficiency of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.